A warm welcome to another episode of SciencePunk Explains the Frame Budget Approach. So, in our last explainer, we were asking, okay, which quantity are we actually tracking here? But that immediately brings up the next big question. Once you've given something a name, how do you know it's, physically real? When is a concept more than just a nice word? Or, to put it more formally, when is it operationally well-defined? Okay, so here's what we've got on tap. We're going to look at why just having a good idea isn't always enough. Then we'll dive right into the solution, the operational definition. We'll check out some real-world examples, see how this sharpens up our FBA toolbox, and then, we're going to touch on the biggest challenge of them all, time. All right, first things first, we've got to wrap our heads around a really critical problem in physics. See, you can have this absolutely brilliant, super intuitive idea, but if there's no way to actually get your hands on it, to measure it, then that concept just stays, soft. It's too vague, too fuzzy to actually build a solid theory on. I mean, think about it. We throw around these powerful words all the time, right? Words like irreversibility or randomness. We spot a pattern and bam, we slap a name on it. But here's the thing. A name isn't an explanation. Not really. It's just a starting point, a label. If we want to do physics with these ideas, we have to go way deeper than that. And that's really the heart of it. We can cook up the most beautiful formulas, come up with the most elegant names, but none of that magically makes a concept physically real. What we need, what we absolutely have to have, is a bridge, a solid connection between our abstract ideas and the messy, concrete world of actual measurement. So how do we build that bridge? Well, that brings us to the solution. It's this beautifully simple yet really profound tool called the operational definition. This is the thing that takes us from a soft idea to a really robust piece of physics. Now, don't get me wrong, this isn't some airy-fairy philosophical concept. No way. This is the key that literally unlocks a quantity, so we can do physics with it. An operational definition basically says this. You want to talk about, say, length? Awesome. Tell me, exactly, step by step, how are you going to measure it? Because that procedure, that is your definition of length. It forces us to ditch the fuzzy stuff and come up with a clear, repeatable recipe. So you can see the shift in thinking right here. We're moving from the left column to the right. We're going from a soft, theoretical word, which is really just a name for a pattern we've noticed, over to a robust operational quantity. And this new quantity, it's defined by a concrete procedure. And because of that, it gives us a measurable result, something we can actually test, something we can compare, and something we can build real theories on. Okay, enough theory. Let's make this super concrete and look at how this works in practice. And you'll see, we use these things all the time, probably without even realizing it. The key thing to remember here is that any measurement, it's a real physical process. It's a whole chain of events, right? You've got some kind of instrument. It has to interact with the system. Then you get some kind of readout from that interaction. And then, a lot of the time, you do what's called coarse graining, which is really just a fancy way of saying you might average the result or simplify it to pull out the info you actually care about. That whole chain, from start to finish, that's the operational definition in action. I mean, seriously, think about it. What is length? It's the procedure of using a ruler. What's temperature? It's defined by watching mercury expand in a thermometer. What's a count rate from a particle detector? It's literally just counting the clicks you hear in a set amount of time, your observation window. In every case, the procedure is the definition of the quantity. And this isn't just for everyday stuff. This exact same logic stretches all the way to the most cutting-edge quantum physics. Take a look at this. What do we even mean when we say signal in a setup like this? Well, it's defined by this very specific, explicit protocol. You have a detector that interacts with one qubit, something gets transported over to the other one, and then a registration event happens. That whole physical process, the coupling, the transport, the detection, that whole shebang is the operational definition of signal right here. Okay, so let's bring this all back home. How does this really powerful idea sharpen the tools we've been building in the frame budget approach? Well, the frame budget approach takes this idea of being operational incredibly seriously. I mean, it's right at its core. In the FBA, what's visible isn't just, everything that's out there. No, it's only what we can actually access. And how do we access it? Through a real physical coupling, using a specific protocol, and always with some limited resolution. So an FBA frame, you can think of it as an operationally reachable slice of reality. And what that means is that all these key terms we've been talking about in the FBA, Things like a minimal event, the budget, an admissible channel, none of them can just be abstract names on a page. They absolutely have to be tied to distinct real-world procedures. Their very definition comes from what we do to measure or distinguish them. Let's take budget again, which we've talked about a lot. It's not some kind of mystical substance or an ontological fluid flowing through the universe. No, not at all. Operationally, it's defined as the accountable, the trackable part of a change in state. It's just the bookkeeping, really. It's keeping track of what gets carried from one step to the very next. Okay, so if we take this rigorous operational way of thinking and follow it to its logical conclusion, well, it forces us to square up against one of the deepest, most fundamental concepts in all of physics. And here it is. This is the huge, profound question that this whole approach just forces us to ask. If every physical concept needs a procedure, if every quantity requires an operational definition, then what's the procedure for time? How do you measure time itself? This is where the FBA does something pretty radical. Instead of just assuming there's this big universal clock ticking away in the background for everyone, it doesn't. It starts somewhere much more basic. It starts with a sequence of discrete actual update steps, distinguishable changes. And here's the core insight. In the FBA, the step index is just that. It counts the updates. It's not counting seconds. So time, the thing we measure with our clocks, isn't some fundamental given. It has to be constructed. It emerges from a more basic procedure, which is the accumulation of internal budget flow inside a system. And what does that mean? It means that even time itself has to have an operational definition. Okay, so let's wrap this up. What are the big takeaways? 1. A physical concept is only really robust when it's tied to a specific measurement procedure. 2. Operational definitions are that crucial bridge between our abstract ideas and the real, measurable world of physics. And 3, the FBA takes this idea and applies it rigorously to its core quantities, which forces us to rethink even gigantic concepts, like time. And that's exactly where we're going next time. We're going to apply this exact kind of sharpness to one of the biggest concepts of all. What is time really, if we do not simply assume it as a flowing background? Hope you'll join me for that one. Bye for now, and stay curious.